Hi. Today we'll be talking about representations of functions as power series. Okay, so we learned in the last section that a power series is basically a series where each term has x to the n or x minus a to the n in it. Well, we can think of those power series as representing other functions that we're more familiar with. And the main example that we'll start with, this is the key example. You'll remember when we spoke about geometric series, n equals 0 to infinity of r to the n. Okay, there was a way to sum this up. This was equal to 1 over 1 minus r, as long as r had absolute value less than 1. The same is true when r is equal to x. And we treat x as a function. Okay, so with x inside of that interval, the function 1 over 1 minus x can be written out as this power series. You might ask, why would we want to do that? We have this perfectly nice compact form for 1 over 1 minus x. But you'll see that there's a lot of advantages to having a function in power series form. Okay, so this is one function, but how can we adapt this to other situations? Okay, so let's adapt this formula. To the following example. Okay, for 1 over 1 plus x squared, I can think of this as 1 over 1 minus x squared. Okay, and now treating this as the input to the power series, I can write this as the sum from n equals 0 to infinity of minus x squared to the n. Okay, if I want to simplify this to look more like the power series we're familiar with, get n equals 0 to infinity minus 1 to the n, x to the 2n. Okay, having 2n there might feel a little unfamiliar, but you can just think about this as only the even terms have non-zero coefficient. Okay, it's okay to have terms that are left out. So here you're not going to have x or x cubed. Okay, if you want, we can write out a few terms. You know, the n equals 0 term will just be 1. Then the next term will be minus x squared. The next term will be positive x to the 4th, etc. Okay, so we have that alternation and skipping powers. And that's the power series for 1 over 1 plus x squared. What would the radius of convergence be here? Well, we're dealing with the sum of minus 1 to the n, x to the 2n. So we have essentially our radius in this is a geometric series with radius equal to minus x squared. So all we need is that the absolute value of minus x squared is less than 1. Well, that's equivalent to saying that absolute value of minus x squared is just x squared is less than 1, which just means that the absolute value of x itself is less than 1. Okay. Let's look at another example. What if that the denominator doesn't look like 1 plus or minus something. So what if we have something instead that looks like 1 over x plus 2? Okay. Well, what we can do here is we can factor out 2 from the denominator. So we'll take 1 over 2 times 1 over 1 plus x over 2. Okay? It's just factoring out 2 from that denominator. 2 becomes 1, and x becomes x over 2. Okay? And this is of the familiar form of 1/2 times the sum, n equals 0 to infinity, minus x over 2 to the n. Okay. Simplifying this expression a bit more, we have minus 1 to the n, x to the n, divided by 2 to the n, where n goes from 0 to infinity. And if I want, I can put the 2 inside so that it looks like this. N equals 0 to infinity, minus 1 to the n, x to the n over 2 to the n plus 1. Okay. So here we're able to just factor out a constant from the denominator to make that expression look more like 1 minus something that we can turn into a geometric series. You might want to put your power series somewhere that's not exactly at 0, right? Remember that a power series can be centered at any a so we'll have, it can be written as the sum of c sub n x minus a to the nth power. Okay, so how can we use our formula for a geometric series if we want this to be centered somewhere else? Let's try an example. Okay, suppose we want a power series centered at a equals 2 for 1 over 1 plus x. Okay. So the key here is to first add and subtract things to get our x to have the expression x minus 2, x minus a, which in our case is x minus 2. Add and subtract to secure x minus a. Okay, so for us, 1 over 1 plus x is the same as 1 over 1 plus x minus 2 plus 2. Okay, and this is the expression that we want, so we can group this as 1 over 3 plus x minus 2, which has a constant plus the expression x minus a that we're interested in. So how do we get this to look like a geometric series? Well, we can then factor out a constant to obtain the form 1 over 1 plus u, where u is some expression. So for us, 1 over 3 plus x minus 2 equals 1/3, okay, factoring out the 3 from the denominator, times 1 over 1 plus x minus 2 over 3. Okay? So from 1/3 times 1 over 1 plus x minus 2 over 3, we can put the geometric series formula to work. So 1/3 times 1 over 1 plus x minus 2 over 3 equals 1/3 times the sum from n equals 0 to infinity of minus 1 to the n, x minus 2 over 3 to the n. And that's just equal to 1/3 times the sum of n equals 0 to infinity, minus 1 to the n, x minus 2 to the n divided by 3 to the n. If I want to simplify a bit further, I'll get the sum from n equals 0 to infinity of minus 1 to the n divided by 3 to the n plus 1, bringing in that third, times x minus 2 to the n. Okay, so that's excuse me. That's another example where we use the geometric series to express a function as a power series. Okay. So we can also use this strategy when we have a numerator besides 1. Okay. So if we have, for instance, x squared over 1 minus x to the 4th. Okay. So this is equal to x squared times 1 over 1 minus x to the 4th. And this we know is x squared times the sum from n equals 0 to infinity, x to the 4th to the n. And applying that nth power, we get n equals 0 to infinity of x to the 4n. I can actually move that x squared back into this series. Okay, you just make sure you multiply each term by the x squared, because multiplication distributes over addition. And you get n equals 0 to infinity of x to the 4n plus 2. Okay, if you want to see what's happening in terms of the terms of the series, here we have x squared times 1 plus x to the 4th plus x to the 8th, etc. And that becomes equal to x squared plus x to the 6th plus x to the 10th, etc. Okay, that's all that's indicated by these two sides of the expression. Okay, so that's a lot of geometric series. Now let's apply one new trick. Okay, we're going to take derivatives and integrals of power series. Okay, so suppose f of x is given by a power series c sub n x minus a to the n, where n goes from 0 to infinity. And suppose this has radius of convergence r. So we can say x minus a must be less than or equal, let's say less than r. This is the radius of convergence. And we'll hold judgment on the endpoints. Okay. So we can take a derivative of this power series as follows. So derivative of f of x is just the sum of the derivatives. So we'll take sum n equals 0 to infinity d dx c sub n x minus a to the n. Applying that derivative term by term, we get n equals 0 to infinity c sub n times n x minus a to the n minus 1. Now we should be careful, because for x minus a to the 0, this term just vanishes. So this becomes n equals 1. Okay? Because constant term vanishes. Okay. How about integrals? For the integral, we take the integral of f of x dx to be equal to, once again, just the sum of the integrals of all of those terms. The sum of the integral of c sub n x minus a to the n dx, and goes from 0 to infinity. And this, is the power rule, so we get n equals 0 to infinity of c sub n x minus a to the n plus 1 divided by n plus 1. And then after this series, we also get a constant of integration, which is what you would expect when taking an indefinite integral. Cool. So let's see this in action. Oh, one other point. Both the derivative and the integral have the same radius of convergence. Okay. But the endpoint behavior may be different. Okay, maybe the function itself converges, but the derivative diverges. That can happen. Okay, so let's see this in action, taking these derivatives. So let's calculate or compute the power series for 1 over 1 minus x quantity squared centered at a equals 0. Okay. So when we're doing this problem, what we want the key is to notice that 1 over 1 minus x squared is equal to the derivative of 1 over 1 minus x. Okay, you can check that for yourself. But we just stated how you can take the derivative of a power series, and this is a function that we also know as a power series. So let's take the derivative of x to the n, which is the power series associated to this function. And that's going to be equal to the power series from n equals 0 to, again, we made the same mistake, n equals 1 to infinity of n x to the n minus 1. Okay? And if you want, you can also write this as the sum from n equals 0 to infinity of n plus 1 times x to the n. Okay? And here all I'm doing is shifting the index of the series so that wherever I see n here, I just put n plus 1. So now there's n plus 1 down here and n plus 1 minus 1 up here, which is what gives us that x to the n. let's do another derivation integration problem with power series. Suppose we want to compute a power series for ln of 1 plus x. Okay, and again, we're centered at 0. Okay, how would we go about this? Well, we'll take notice that log of 1 plus x is the integral of 1 over 1 plus x dx, right? So again, we know how to take the integral of a series. This series is the integral of n equals 0 to infinity of, for this series, minus x is the ratio, so we have minus 1 to the n times x to the n dx, and we integrate term by term to obtain n equals 0 to infinity minus 1 to the n divided by n plus 1 times x to the n plus 1 plus c. Okay? We can shift this series up so that we're starting at n equals 1, so that we can just have x to the n, and it looks a little more normal. Then we'll get n equals 1 to infinity minus 1 to the n minus 1 divided by n times x to the n. Okay, and then I still have that constant of integration. How can I figure out what this c is equal to? Well, I know that log of 1 plus x is equal to c plus this expression, this power series, for all values of x in the radius of convergence, which we know just by looking at this problem is 1. So if I set x equals 0, what I'll obtain is ln of 1 equals c plus a whole series of zeros. Okay, so it's just ln 1 equals c, but that means c is just 0. So ln of 1 plus x equals the series n equals 1 to infinity minus 1 to the n minus 1 divided by n times x to the n. Okay, let's do one more example. This last example uses arctangent to approximate pi. So the first step is to find a power series for arctangent. Okay, well, what do we know about arctangent? It's the integral of 1 over 1 plus x squared dx. Okay, so that's a geometric type series that we're familiar with. We can write this as the sum of minus x squared to the n dx, where n goes from 0 to infinity. And that's just equal to, we'll simplify, we can integrate term by term. We'll get n equals 0 to infinity minus 1 to the n, x to the 2n plus 1 divided by 2n plus 1. Okay? That's what you get when you integrate this series term by term. So the next step that he does to approximate pi is first you have to notice what's the radius of convergence here. The radius of convergence is equal to the same as the radius for 1 over 1 plus x squared, which is 1. Okay, so given that our radius of convergence is 1, we want to take a value of x, which is smaller than 1, and which gives us some multiple of pi in its arctangent. So find x with absolute value of x less than 1 and a well-known arctangent value. Okay, and so in our case, we're going to take x equals 1 over the square root of 3. Okay, if you remember your triangles, 1 square root of 3, 2, so this angle will be, it's this angle. This angle will be given by pi over 6. Okay? So arctangent of 1 over the square root of 3 equals pi over 6. But then on the other hand, we have this expression, this power series expression, where we can plug in x. So we also know arctangent of 1 over square root of 3 is equal to sum from n equals 0 to infinity of minus 1 to the n, 1 over square root of 3 to the 2n plus 1, divided by 2n plus 1, and that's going to be equal to pi over 6. Okay, simplifying this expression and multiplying both sides by 6, I'll get pi is equal to 6 divided by the square root of 3 times the sum from n equals 0 to infinity of minus 1 to the n divided by 3 to the n times 2n plus 1, which I think is a really fun identity, and it comes out of relatively simple power series computations. Okay, I think that's it. Thanks very much.